So for everyone who was here last month, I did an introduction to Streamlit. And this month, I'd like to do an introduction to graph databases, specifically Neo4j's implementation of a graph database. And if this is all hopefully in the future, I can do one where I'm showing how to use Streamlit and graph databases together to make very awesome spaghetti hands and hopefully an interesting demo. Okay, so in full disclosure, obviously I am a developer advocate for Neo4j, which is why I'm kind of showcasing Neo4j's implementation of graph databases, although I'll only be kind of talking about it a little bit toward the end. So that's what I do for my day job. Night job is a list comprehension of using Pythonista, which is why David and Diane let me do some talks on occasion. Okay, so we'll jump right into this because I've got I think 10 minutes. Okay, so graph databases. Why do we even care? Because graph databases, according to this Gartner analyst, in the next couple of years, the overwhelming majority of data and analytics innovations will happen within the graph technology space. So if you're using a graph database, that will get you a foot in the door. This prediction is supported by this very graph-friendly chart from DB Engines showing the popularity changes between different databases. You can see here at the very top, the green is the graph database category, and you can see it's climbing very quickly. And also in the last couple of years, time graph databases, completely different topic, but that's also climbing. So expect to hear more about both database types in the next couple of years. Now, graph databases, what I really love about graph databases, there are many great things about it, but is you don't have to do traditional SQL joins, right? Like if you're doing some really complicated recommendation type engines, you don't have to navigate the inner, outer, inner, full join soup of options. And that alone is probably why I started using graph databases a few years ago. So anyways, okay, so reasons why you would want to be interested in a graph database. Now, the reason you can kind of walk away from the joins, but not the outcome of the joins that you want, is because of the way graph databases store data, right? So you can imagine graph databases as basically a bunch of circles and arrows, right? And in graph theory, these are known as vertexes and edges. And in Neo4j's implementation, they're specifically known as nodes and relationships, right? So you have a node, which is analogous to a row in a table. And then that is connected to another node or another row in another table. And they're connected by this relationship, right? And the relationships are normally, you would think of them as the joins in SQL queries, right? So they're the query, they're temporary pieces of information joining 2 bits of data. But in graph databases, that's part of the data store. Okay, so let's dive in a little bit deeper here. So nodes and relationships can be given labels and types. So nodes can have several different labels. In this case, we can say like one node is a person, this other node is a goal that this person is trying to seek, right? And seek is the type of relationship for this data. Okay, so if we put some context into this, we've got King Arthur, and he is seeking the Holy Grail, right? The name for these 2 different nodes is King Arthur, Holy Grail. And a great thing about graph databases is you can add properties to the relationship, right? So here we can basically weight the relationship, right? Like how long has King Arthur been searching for the Holy Grail? Or how much intensity is King Arthur looking for the Holy Grail, right? You can put that value into the relationship. Okay, and again, because relationships are part of the graph database store, they're basically first-class data citizens of the database, right? Versus an SQL database where the joins are very temporary. They're not part of the permanent data store. Now, when the relationships are part of the permanent data soup, it allows you to do interesting things very quickly, right? You can traverse data within the graph very quickly. So if you're trying to find who friends of friends of friends are, you can do that in the graph very quickly, right? So you can do path finding quickly. So you can, which is related to like route finding or finding the quickest way from A to B, right? Which is route finding. The graph architecture is also easily, easily integrated with more advanced data science algorithms like link prediction, centrality, page ranking, community detection. All these sorts of algorithms are fairly easy to apply to your data inside a graph database. Okay, now the current graph database landscape is quite large, right? So the modern graph database space has been around for about 10 years. Neo4j was one of the first into the space, but a lot of other companies have come into the area with lots of variations of technology, which is great. So like here, like dgraph may be of interest to people who are used to GraphQL. Their entire query language is just a GraphQL query language, but everyone else has got some other query language, which brings us to kind of a working part of graph databases. There is no GQL standard yet, right? There's no graph query language like we have for SQL. There is a working group working on the GQL, and this sample of query languages is a sample of all the available graph query languages that are out there. But these are the languages this working group is using as reference for creating this future graph query language. Okay, so of these languages, the one I'm going to kind of focus on is Cipher, which was originally developed by Neo4j. And Cipher is the open source version of Cipher. Neo4j continues to develop its own commercial version of Cipher, but the differences are not massive. Okay, so this is an example of what Cipher looks like. If you're used to SQL, you'll see that it's considerably different. It's very ASCII art-esque to help you sort of kind of mentally noodle relationships a little bit easier, right? So this query here is just asking match, which is similar to select, or find. Like so, match a person node in this pattern, right? A person that knows another person, where the first person, the first node, their name property is King Arthur. So what this would return from a Neo4j database or any database running Cipher is King Arthur and, oh, well, I have to add a return statement, but it would return King Arthur and then everybody he knows, right? And this pattern that you see, person knows M person, you can keep making this pattern longer, right? So you could say like, okay, whoever this person knows that other person who happens to work at this other company, who sent an email, and who received that email. So you could put this long chain of pattern, and you can return that whole chain or bits and pieces of that that chain of languages. So, and you can stack these together and kind of collect, unwind, and run basic math on basically functions on that stuff, all within kind of a dense Cipher query. Okay, so that's a Cipher query language. Okay, so still okay on time. So Neo4j has an official driver that we produce and continuously maintain so that it can connect with our backend. So the Python driver works in kind of two parts. The first part is you're initializing a driver, and then you use a context manager to run a session. The session manages itself in terms of like retries or error handling. And to make this work, it uses static transaction functions. So that's the second part, right? The transactions. And that's where the Cipher query goes, right? So you have this query, and then you have any bounded parameters that go with the query, and you run that through the transaction. And then whenever it completes, it will go ahead and complete that session. Okay, so all right, if anybody has questions, you can ask me in the chat or ask me after I'm done here. Okay, so this is generally how the Python driver works. There are community libraries that kind of stack on top of this to provide like OGMs for data science use. And there are query builder libraries like Simple, which, so if you don't know Cipher, you can use the Simple package, and using Pythonic commands with auto-completion will basically create a function call that is more readable to a Python user, and it will convert it to the correct Cipher query that you can then just dump into this call. Okay. All right, so not really a demo, but just kind of showing you the bits and pieces of how this all kind of works. Okay, so what we're looking at here is the Neo4j Aura instance, right? This is the cloud managed instance. And when you create a database, you can see here on the left here, maybe you can't, there is a connect Python tab. And here we've provided basically the boilerplate code you would need to get started with Python, right? It contains 2 Cipher transactions for creating some nodes and relationships and for retrieving. And then some, basically creating this class that you can kind of copy, paste, and manipulate. Okay, so what I've done is I put this into a simple Python app here. And I have basically put in my credentials for this cloud instance. And let me show you this instance here. So in here, this is the general command for give me all the nodes that you have. There should be nothing in here, right? So no records. Now, if I go to the Python app, and I'm using poetry, run Python 3, Neo4j, and app.py. Yes, okay. So what this should do is it will just call these functions that were part of the boilerplate to create 2 nodes, one that's going to be called King Arthur, and the other one Sir Lancelot, and then just find the person King Arthur. Okay, so here, created the friendship, and did I turn off? Oh, I got rid of the print statement. Okay, so if I put in, oh no, your found person, King Arthur. Okay, so I'm not sure why so the console log showed that it created the friendship, and we can just check in the database here. Oop. Oh, yes, we need to actually run the query. So here we've got Sir Lancelot and King Arthur. And I can actually, oh, well, okay, so both people are in there. So if you were to run a match, let's do person, where, and name equals Arthur. Oh, return. And here n is just a variable assignment. So I could use any letter there. Okay, so it returns the single King Arthur node. Okay, I think that's my 10 minutes. Okay, so if anyone has any questions, or if you want to contact me, you can contact me here, or just ping me on Meetup. But yes, does anyone have any questions?
There was 2 questions in the chat. I don't want to jump the gun and repeat them for other people, but I'll do that anyway, actually. One was, how are Neo4j's offerings different than, say, Amazon's hijacked offerings? I don't know what that means, but maybe hijacked offering.
Okay, yeah, I know Amazon has, I forget, was it, not Nebula, but they have a graph data offering using the Gremlin query language. So I haven't heard of hijack, so I'll take a look at that and hopefully I can get back to you regarding that. And oh, thank you, Alan. And Jeremy, so yes, you can speed up the query. So, obviously I use doing a very simple setup. So you can add constraints and indexing to increase the performance of the database. And then there's lots of little tweaking you can do with Cipher to make it faster. So built in, we have Cipher calls for analyzing the query that you run. So you can, I think they're called analyze and then explain, right? So it'll basically walk you through like what the query and the database are doing when it's making the calls. So you can make tweaks to try and, reduce the number of calls and hits that you're doing against the database. So yes, there are processes for that. Namespaces, for instance, SparkQL uses URIs. Oh, namespaces in terms of, let's see, right, Spark uses URIs. I'm trying to remember why they do that. So, for the nodes, right. So, no, it doesn't use URIs for differentiating between nodes. And so when you create a node into the database, it's basically given a temporary ID, which you shouldn't use for production. But you can create a unique property and use that as a unique identifier, if that helps.
Cool. Any last questions before we move on? Oh, there is a big one from Jeremy.
Yes. The speed is noticeably different if you query graph over 10,000 nodes. Is there such a limit in Neo4j?
Just to read the question out loud, I
Yeah.
noticed that Network X, a graphing lib based on Python dictionaries, fast for small projects, not possible for mid-large scale projects,
Oh.
that the speed is noticeably different if you query over 10,000 nodes and edges. Is there such a limit in Neo4j?
You can set the limit for node returns for your queries. And there are other like after parties technologies that have stacked on top of Neo4j to allow you to query really large data sets, but then have it basically summarize it or make it more palatable to make it easier to query that stuff.
Is there a way to cluster these Neo4j databases like you can with Postgres or something like that?
Yeah, so we do have casual clusters. So yes, yeah, you can scale it up. And Marcy said, what are some interesting example use cases for this? Oh, okay. So this use case is what actually got me onto Neo4j years ago. So the ICIJ, the International Consortium of International Journalists, when they released the Panama Papers, well, before they released the Panama Papers, they used a system built on top of Neo4j for all the different journalists around the world to piece together information and to kind of query this giant data dump that they got. And using, graph technology, using Neo4j, they were able to basically piece together who was who in this giant, basically, conspiracy. No, not conspiracy. The other C word. Anyways, the entire web of fraud that was going on. Cartel? Yeah, I think the cartel was also involved. But so for fraud detection, basically, fraud detection is a great use case for graph databases or graph technologies because fraudulent behavior sort of naturally kind of sticks out from other behavior for a given person or a given group. And it's also easier to find people who are trying to hide themselves, right? Because, one person can only be in so many places using so many different technologies, talking to so many people. So things like link prediction are really good at going, okay, there's some mastermind over here that we can kind of like the database is telling you it should be there and what nodes are close to it. These are the things you need to go look deeper into. So like investigative journalism is a good one. Healthcare is also a great space. Obviously identity resolution. What haven't else I said? God, there's a ton of use cases, but those are probably the top ones that come to mind. Fraud in healthcare. I haven't heard that particular use case. So like healthcare and like biosciences, right? Like I know a lot of like so for healthcare, things like figuring out, like what certain things may be affecting people's outcome. Like, is it, they're from home to ambulance ride to how long they were in the ER, right? You can put all that sort of data in and sort of start getting a sense of, how you could improve healthcare services, and fraud more like what insurance fraud? So like financial type fraud or credit card companies would use graph databases for finding these sorts of things out. Let's see, I'm envisioning the push pin board in every TV. Yes, exactly. So yeah, imagine that, what is it, like a crime board where the detective, and I guess no detective in the real world, puts, photos of people, tying strings to people. But that's basically, that is a graph database, right? Just take that and scale it up to, millions of nodes and tens of millions of relationships. And then you've got, something that's like a knowledge graph or something that happens internally. Recently I met someone who works at Illumina who's trying to build a knowledge graph of basically knowledge within the company, right? So finding all the people who have specialties and who they're all working for, so that if you're doing something, you want to find a specialist or specialists who work on something, you can traverse this knowledge graph and find the people internally that you want to talk to, or the documents that you need to find. Oh, cool. Okay, I've probably used up more than my fair share of time.